Hello everyone. The next topic to be discussed in diodes is the capacitances of diode. That is important from examination point of view. There were questions on this in GATE, engineering services and civil services as well. The capacitances of diode, basically there are two types of capacitances of diode called the diffusion capacitance and transition capacitance. We will talk about both of the capacitances one by one. First we will talk about transition capacitance, which plays an important role in reverse bias mode. So first I'll do the transition capacitance. Remember, I repeat it again, the transition, why the capacitance is existing in a diode. You please see, our diode has the bound charges stored in the depletion layer. If this is P side, this is N side, the P side has negative bound charges stored in the depletion layer and N side has positive bound charges stored in the depletion layer. If there are bound charges stored in the depletion layer and width of the depletion layer is W, then it must be possessing some capacitance. The capacitance of this depletion layer, I repeat, the capacitance of depletion layer is nothing but transition capacitance. It is also called space charge capacitance. It is also called junction capacitance. So the transition capacitance or junction capacitance or space charge capacitance of a diode is nothing but epsilon A by W. Please do remember this. Epsilon A by W, just like your parallel plate capacitor. What is the capacitance of a parallel plate capacitor? It is just like a parallel plate capacitor like this, where W is the separation between the plates. So capacitance of a parallel plate capacitor will be epsilon A upon W. So the expression is similar to a parallel plate capacitor. Epsilon A by W, that is how you can remember. Now, what is epsilon? Epsilon is permittivity of this semiconductor material. Fine. So you should remember the permittivity of semiconductor material is what? Epsilon naught into epsilon R. Epsilon naught is the permittivity of free space, that is epsilon naught is equal to 8.85 into 10 raised to power minus 12 farad per meter. I hope you know. And this epsilon R is called relative permittivity of this medium. Permittivity of what? This medium, that is semiconductor. So you should remember this relationship. Please try to recall, we have studied the depletion layer width. The depletion layer width of a parallel plate capacitor is 2 epsilon upon Q multiplied by 1 upon NA plus 1 upon ND. This is very important expression. I repeat, you have a lot of questions. We have already discussed this topic. We have already derived the expression of depletion layer width for different biasing conditions. This is what I have. So since this CT is inversely proportional to W, so what will happen? This CT will be inversely proportional to 1 by J 1 by 2. But remember, this expression of capacitance, this expression of depletion layer width is applicable for which type of junction? For abrupt. Please do remember that, for abrupt, or that is also called step graded junction. When there is a sudden change in concentration of the charge carriers or bound charge density across the junction, that is called step graded junction. So in case of the step graded junction, the variation in transition capacitance is 1 by Vj root. And you can see this is Cj is proportional to what? Vj minus 1 by 2. That is for what? For step graded or abrupt PN junction. Please do remember this. This is very important. Fine. Now we know what is Vj Vj, I have already given you the expression. Vj is nothing but V naught for open circuited junction. When junction is open circuited, it is V naught. This is V naught plus Vr for what? For reverse biased junction. I hope you remember that. And this Vj is V naught minus Vf for forward biased junction. Please remember these three relationships. Vr is what? Vr is reverse biasing voltage of the diode. Vf is forward biasing voltage of the diode. So if you see, this W is applicable for all the biasings. So the transition capacitance will be existing for all the biasing, that is for open junction, for reverse bias junction, for forward bias junction. But if this is small, this will be, if this is small, this will be large. So the capacitance, please do remember, what is the reactance of a capacitor? 1 by j omega C. So smaller is the value of C, larger will be the reactance. So for this, larger will be the reactance, forward bias. But remember, the transition capacitance plays an important role in reverse biased PN junction. Why? Because reactance in that case will be small. Reactance offered by the junction to small signals will be small when C is large, and C is large when W is small. W is small when this, you can see W will be small when V is small, or you can see this relationship here, XC, when C is small, when C is large, XC will be small, C will be large. In which case, you can see when this is large, this is small. Vj is large. Vj is large when this is reverse bias. Vj is large, C is small, C is small, Xc is large. What I mean to say is, when you have the reverse bias PN junction, the width of the depletion layer is large. Width of the depletion layer is large, charges stored will be large, more. If charges stored are more, capacitance will be more. So capacitance, transition capacitance is high when the junction is reverse biased. So do remember, the transition capacitance plays an important role when your PN junction is reverse biased. So there can be questions on this in the exam, but remember, this Vj, this W is directly proportional to Vj power 1 by 3, for which? For linearly graded junction. What is the meaning of linearly graded junction? When the concentration of the charge across the depletion layer varies linearly, not suddenly. That is called linearly graded. As far as exam is concerned, till now questions have appeared only on step graded, but you should remember, for engineering services objective type paper, there can be question on this relationship. Otherwise, most of the times it is 1 by 2. We always consider step graded junction as far as your mathematical analysis for examination point of view is concerned. Now, there is second type of capacitance in diode, that is called diffusion capacitance. Remember how this capacitance come into picture, whether it is transition capacitance or diffusion. Whenever there is storage of charge, maybe anywhere, you have a charge in the air here. If there is a charge, positive charge, its image will be formed on the ground. Negative charge will be induced below the positive charge on the ground. And if there is separation between the two charges, even in the space in this air, there will be a capacitance. So whenever there is a stored charge, there has to be a capacitance. We are talking about capacitance in diode, so there must be some charges stored in the diode, then we talk about the capacitance. So first capacitance, first charge stored is in the junction, we have seen. On N side it is positive bound charge, on P side it is negative bound charge. Because of that, the junction depletion layer behaves like what? A parallel plate capacitor, and that was the capacitance, which is transition capacitance. The second type of capacitance in a PN junction diode is diffusion capacitance. So let us talk about the diffusion capacitance. Before I talk about diffusion capacitance, we need to understand the concept that what is that charge stored to understand the diffusion. This type of capacitance plays an important role in forward biased PN junction. Remember this. I repeat, the diffusion capacitance plays an important role in forward biased PN junction. So when PN junction is forward biased, there must be some charge stored other than the charge stored in the depletion layer. In depletion layer we have seen the capacitance, so there is another capacitance which is coming into picture, that is diffusion capacitance, and this is not the transition capacitance, it is some another capacitance which is coming into existence. Let us take the layer diagram of PN junction which is forward biased. This is a PN junction diode which is forward biased. This is the junction area. This is depletion layer on P side, this is depletion layer on N side, this is P, this is N. I will assume one thing, I will assume that P side is heavily doped as compared to N side. I am assuming Na, that is acceptor concentration, is much greater than Nd, and we have already seen when P side is heavily doped as compared to N side, most of the depletion layer lies on N side. So what happens to the charge carriers? Please do see this. We will study the variation in the charge concentration across the junction. In case of a forward biased PN junction, what happens? Let us see the concentration. If P side is heavily doped as compared to N side, we have seen in case of forward biased PN junction, that is variations in concentrations. So the concentration of holes will be like this, it will be reducing exponentially like this across the junction, and it remains constant here. This is W, this is X, fine. This is X equal to 0, this is X equal to Wn, this is X equal to minus Wp. This is Wp, this portion of it, this is Wn. If you talk about concentration of electrons, that will be reducing exponentially, but since this is lightly doped, this is heavily doped, so when holes are diffused across the junction, this is forward bias, when holes are diffused across the terminal, these are diffused on this side, holes on this side become minority carriers, and when these are minority carriers, the concentration will, these will be diffusing towards this cathode. This is called cathode, this is called anode terminal. So their concentration will decrease, and finally at far end it will become equal to Pn naught. Here it is maybe Pwn, that is concentration of holes at this. Fine. Concept is clear? Similarly on this side, please do see one thing here. What I have, when holes are injected on this side, there is excess charge coming into picture. That excess charge or the concentration at thermal equilibrium on N side is Pn naught. Concentration of electrons on this side is nothing but Np naught. But there is additional concentration which is nothing but additional charge carriers which are coming from N side. These are electrons, additional electrons. Similarly, the holes coming from this side, this is called excess minority carriers. Please remember, when holes are being ejected, the concentration at holes will be large here. Concentration of holes is large. And when it moves towards this, so these will be diffusing and increase exponentially. And at far end, the concentration will become Pn naught, that is called thermal equilibrium concentration or concentration of charge carriers, minority carriers at thermal equilibrium. Similarly on this side, electrons are injected on this side, this is called minority carrier injection. Electrons from this side are injected on this side, so this is minority carrier injection. But since this is lightly doped, so concentration of electrons is not to that level. Now what is happening? Continuously holes are being injected from this side, electrons are coming from this side, so there is recombination taking place, and this is the excess charge which appears to be continuously stored near the junction on this side. Since I am assuming this is heavily doped, this is lightly doped, so most of the charge is stored here. This charge is small. Clear? Now the current, forward biased current of this diode is function of this charge, and that is given by I equal to Q by tau P. Please remember this. Similarly, I can find here Q by tau N, and that will be Q dash, nothing but charge of electrons. You can find total current will be sum of these two, but I am assuming this is heavily doped, this is lightly doped, so most of the charge is stored here. This is negligible, I will neglect this charge. So the forward biasing current of the diode, that is I, is nothing but Q upon 2B, that is mostly determined by the minority carrier holes stored on N side near the junction area. I repeat, the forward bias current of diode is the function of excess minority carriers stored near the junction area. I is equal to Q upon tau P, where tau is what? Average lifetime of holes, average lifetime of minority carriers, that is holes on N side. Similarly, you can find in terms of electrons, but just for simplification of mathematical analysis, we neglect this charge stored, because most of the charge is being stored on N side. Why? Because this is heavily doped, this is lightly doped. So now what is Q? Stored charge. And this is where it is stored, near the junction area. Please remember, these are the questions for engineering services prelims. Whatever I am saying, each and every point is one question for engineering services examination, and then mathematical result will be the formula for gate exam. Fine. So what is Q? That is access, that is charge. Q is what? Q is, that is charge of minority carriers stored near the junction area. Please remember this. And what is Q? Q is nothing but I into. Please remember this. This is important question formula. Do remember this. This is important, and please do remember this. This is important as far as exam is concerned. Now let us talk about diffusion capacitance. The diffusion capacitance is defined as the rate of change of stored charge per unit change in the voltage. That is nothing but diffusion current. This rate of change per unit change in this voltage across the diode. And this is what? That is d upon dV I into tau P, or this gives what? CD equal to tau P can be taken outside, di upon dV, and you know what is di upon dV? That is dynamic conductance, so that is equal to tau P into G. And you know what was this? Dynamic conductance was what? CD equal to dynamic conductance was tau P ID upon eta Vt. So please remember, this is important expression for your exam. There can be question numerical on it. Now let us talk about the another important fact. What do I observe? The diffusion capacitance is proportional to the forward biasing current of the diode. Fine. When there is no current, there is no diffusion capacitance because there won't be any stored charges. Although when it is reverse biased, there are stored charges, but when junction is not forward bias, rather open circuit or reverse bias, there are no stored charges, there is no diffusion capacitance. So that means this diffusion capacitance comes into it plays an important role, rather it plays an important role when diode is forward biased. So I hope you will remember, when diode is forward biased, it is diffusion capacitance which plays an important role. When diode is reverse biased, it is transition capacitance which plays an important role. Fine. So more is the diode current, more will be charges stored, excess minority carriers stored, more will be the diffusion capacitance. And you can just remember, for engineering services point of view, the diffusion capacitance is inversely proportional to the frequency of the signal. This was case of DC signal. If you superimpose this DC signal with AC signal as well, that is called dynamic diffusion capacitance when you have only DC. But there may be the cases when you apply AC as well, superimpose AC plus DC. In that case, the diffusion capacitance varies inversely with frequency omega. Input signal, less will be the diffusion capacitance. There can be objective type question in engineering services prelims on this. This is important for gate. This is important for engineering services, but this is important only for engineering services. There can be objective type question on this concept. So this is all about your diffusion and transition capacitance of a diode. And this diffusion capacitance can be the dynamic capacitance as well when your diode is superimposed with an AC signal. And we will see the numerical part, but before that I will be discussing another two important topics, that is the equivalent circuit of diode and switching characteristic of diode. After that we will see the numericals on this part, which have appeared in past. So just wait for the next video, and then we will talk and discuss about the different questions from GATE exam.